So yeah, good morning. Thanks a lot, Hans, for the introduction. My name is Leonard Wossnig. I'm the CEO of Rahko, a London-based quantum machine learning company. And I think I tried to, in this talk, more give a kind of step back, and I think it was nice that Peter just asked the question how quantum computing could add value here, because I try to bridge the two communities which I think are attending this conference here. The one, the machine learning for quantum systems, quantum chemistry in general, and the other one, the quantum computing community, and try to see really where's overlaps and where maybe synergies which can be used. Okay, then let me start by giving you a brief overview and of the talk. I will start by recapping kind of briefly what are kind of the computational chemistry methods, and particularly methods which are commonly used in industrial problems and their requirements as a first point. And here particularly will show that for many industrial use cases, we generally need very fast methods because we need to screen through a huge number of candidates, or for example, in ND simulations, do a lot of computation steps. Then I'll next go into quantum computing and kind of check how quantum computing, at least how we currently view it in the quantum computing community, fits into this picture and whether or not it is useful. In particular, I'll show that based on the insights from the first part, quantum computing on its own is probably not sufficient to really help for a lot of these industrial problems and applications because it's not fast enough. And this leads us then over to something which we've heard now, just Alex speaking and Gabor earlier, and I think also Michele Ceriati earlier in this workshop, which is about quantum machine learning, and particularly how quantum machine learning opened up new opportunities here in quantum chemistry over the last 10, 20 years already. And which leads me then to the next point, which is how can we now combine quantum computing and machine learning, or quantum machine learning, to really get the best of both worlds. So, and particularly how this is, I think, in my view, a good long-term strategy. As a final point, I give then some examples of the Rahko research we've done over the last couple of years, and just to point out a few high-level details, but not going into too much. Okay, so let's get started then. So quantum computing has been majoring over the last decade or so, and becoming a quite established and growing field of research. So as such, it has also been promised to solve some of the really big challenges in the 21st century, including renewable batteries, meaning helping to design more better materials, for example, for batteries, or also helping us with faster drug discovery. In order really to understand whether these promises are justified, I think it helps first maybe to understand how these processes are done industrially. This means how do we actually industrially approach discovery processes, for example, for drugs or better materials. And so in order to give you a good understanding of this, I want to go into three details, and these are namely molecular dynamics, virtual high throughput screening, and molecular spectra. And what we see in all of these applications is that we typically need millions or 10 millions even of calculations, meaning that the single point calculation, for example, in molecular dynamics, the forces at each time step, or in virtual high throughput screening, the single candidate, if you want to evaluate such huge volumes of candidates or so many computational steps as an ND simulation, each single calculation needs to be sufficiently fast in order for us to allow to really deal with these immense volumes. And that is a big requirement, because if you want to come up with computational methods which we can use in these industrial processes, we need to make sure that they are hence sufficiently fast for us to be used within this context. So so in summary, we need to perform millions of evaluations and computations, and these need to be reasonably fast and cheap. And this brings us then to what is currently done in existing in computational chemistry. So this graphic I've been taking from Frank Noyes' talk. He very kindly shared his talk from I think last week with me. So I just adapted this. And it's just a brief, very high-level overview of kind of a range of computational chemistry methods which exist today. The important point I want to make here is that if we look at what is used today, in context of what I just mentioned in terms of molecular dynamics or in virtual high throughput screenings, the majority of industrial users used very low level, meaning inaccurate, but very fast methods. And that being said, I know there are examples where higher levels of theory are used. For example, also DFT is used in the end of many crystal structure prediction processes, for example. But the volume of DFT calculations versus the volume of, for example, force field calculations is negligible in terms of the overall computational volume in terms of which is done in industrial processes. So, and that's an important point, because what we see from this is that if we have methods which scale, at the order of n to the power of 3, so typical DFT scaling, maybe these are not as useful as we would wish they are. And it brings us later on to the quantum computing as well, because we need to make sure that the single calculations need to be sufficiently fast for us to really make a big change for industrial discovery processes. Okay, so as mentioned, how does quantum computing then fit into this? And I've here referred to the paper by Ryan Babush and others from 2019, which is, I think, at least to my knowledge, the current state of the art in terms of fault-tolerant quantum algorithms. I have used fault-tolerant quantum computing here because for all the variational algorithms, it's still very unclear how the actual scaling and behavior is, because all of these are empirical heuristical methods. So we cannot mathematically prove their runtimes exactly. While for these types, like the fault-tolerant algorithms, we know the specific runtimes, and hence the n to the power of 3 is roughly the same as DFT for this algorithm. Small addendum here, maybe. I know the actual paper has a dependency on the number of electrons and the number of orbitals, but saying these are roughly of the same order, which I think is a reasonable day, it comes to n to the power of 3 as well. So if you look then at quantum algorithms, we see immediately that while being potentially much more accurate, they're not necessarily much faster. And that's a challenge within the context of these industrial processes, which we just looked at before, right? Because if we want to understand these processes or to really deal with these challenges, we again see that quantum computing and quantum algorithms, at least the current state of the art, is not sufficiently cheap to be used for virtual high throughput screening, or for example, for these long molecular dynamics simulations, because again, the volume of computations of single evaluations is too high. So if you have a computational method which scales n to the power of 3, you need to do millions or tens of millions of these calculations. Quantum computing really doesn't solve this problem. On the other hand, also, quantum computing doesn't seem to be sufficiently cheap to allow us to treat large system sizes. That's one of the other applications where people have hoped a lot from it. So far, so good. So the question is then, can we develop methods which are sufficiently cheap on the one hand side to be really industrially useful, but also maintain this high accuracy? And that's the clear answer is yes, I suppose, although it's still a lot in research. But these are exactly the methods which we heard already from Gabor Ksani and Alexander Tkachenko, Michele Ceriotti, and Anatoly in the next talk as well. And yeah, so in fact, these machine learning interatomic potentials on the one hand, which have been done by Behler, von Lilienfeld, Tkachenko, Ksani, Ceriotti, Müller, Rupp, Scheffler, Noe, and others. But also, particularly on the right-hand side, you see the blue bubble, which are variational quantum Monte Carlo methods based on machine learning. They enable us to, in fact, raise the accuracy and still maintain the low cost of very cheap kind of methods such as force fields. Admittedly, they're slightly higher typically, but still cheap compared to DFT. So just as a simple example here, I took this from the paper here in the bottom, where they're assessing conformal energies. You see that the times, like the computational times of machine learned force fields here, ML, with the orange dots, are comparatively much lower, orders of magnitude lower than DFT-D in this case. At the same time, they still, compared to the red, the yellow dots here, the force fields, the traditional ones, much more accurate. And this is just one example. I know there's cases where the machine learning force fields perform, of course, much better. And yeah, it's still low, as Alex mentioned as well. Depending on the application, there's still a lot of open questions. So yeah, just for the ones who haven't listened to any of the previous talks, I just briefly wanted to recap some of the challenges and opportunities in quantum machine learning, meaning machine learning for quantum systems. So generally, we train the algorithms, the machine learning models on accurate, high quality ab initio data. This means that typically the costs of acquiring a data point are relatively high, and we want to minimize this. So as Hans Priegler just asked as well, people have already used active learning methods. For example, Gabor introduced the COR-based, like lever score-based methods, but there are many others, for example, based on clustering, et cetera, who try to reduce the amount of data which is used to train these methods. However, like evaluating a single data point is still costly, so we still want to really minimize the amount of data we use. So contrary to large data sets, which are now common practice in modern machine learning with neural networks, the focus is still on small but high quality data sets. Anatoly von Nielenfeld, also Big One, mentioned in a paper from 2017, I think, the first version, this possibility of small so-called amons, which are basis sets of molecules. And Frank Noe recently pointed out as well a similar idea that if you would have maybe hundreds or maybe a few thousand of small representative molecules, you might, in principle, if you would gather such a set, be able to predict a wide range of properties for specific compounds. And this brings us then to the following question. So how can we generate these data sets efficiently to overall reduce the computation time? So I think that one of the current state of the art is this classical approach where we kind of use a variational quantum Monte Carlo method, which in combination with deep learning, this is so-called PolyNet. But also, of course, we could use standard GFT or couple cluster methods to obtain high accuracy data. The idea, and that's kind of what I wanted to emphasize in this talk, is in the long term, we could, of course, also replace this generation of the data set by potentially cheaper and more accurate methods via quantum computing. So by generating very small samples of highly accurate, but typically still expensive data sets using a quantum computer, we could indeed combine these high quality data sets with quantum machine learning, and hence enable very fast, accurate, and still cheap, meaning affordable, predictions which are industrially relevant. So just in summary then, if you look at the two different methods, so if you look, for example, at force fields, traditional ones, we know that they are extremely fast and extremely cheap. However, we also know that the predictive accuracy is typically quite low. On the other hand, if you look at quantum computing, again, this n to the power of 3 scaling, which is, I think, state of the art currently, and the best known result, the predictive accuracy is extremely high. However, the speed and the cost is still too high for industrial applications. So in conclusion of the talk, I think for the long term, the perspective of combining these three different ingredients, meaning computational chemistry with quantum computing and machine learning, would enable really to get the best of all the different worlds, and hence combine speed and accuracy in a fashion that is industrially usable and relevant. So yeah, coming back to the initial graphic. So if we put quantum computing and hence new force field machine learning potentials in there, I believe that in the long term, whenever we have sufficiently good quantum algorithms to derive this data, we might be able to push the frontiers in terms of the accuracy of machine learned interatomic potentials a bit further than they are today, and maybe enable hence this fast and accurate and cheap prediction through this combination of these technologies. Good. That's the main point of the talk that I wanted to make. I now briefly give you a couple of things, a couple of details regarding what we're doing research on in Rahko. So, and these include, so yeah, I start by kind of the machine learning approaches for quantum computing. For example, we have been showing that, this is Thomas Rogers' work in our group, that you can, for example, use machine learning methods trained on DFT to dramatically speed up the prediction of molecular spectra. And in fact, once the methods are trained, we obtain on a GPU, we can do roughly 1,000 molecules per second on a single GPU. Other research we've been currently doing, and that was actually advised through Gabor Chani and also Alex Chenko here, is with the team with Edward Grant, Thomas Rogers, Paul, let's say, and Dave McMahon did in our team, is the question whether we can reduce DFT calculations when we want to do virtualized throughput screening, in this case for crystal structure prediction. So in crystal structure prediction, there's a lot of work which has been done by Gabor previously and then others as well in this domain, but it's also something we focus on commercially. So I'll just give you some examples here. We showed that in fact, it is very possible. We can in fact, based on a few hundred of training examples, we can already achieve a very high percentage of the DFT reduction, meaning that if we have a huge amount of candidates here again, we need to screen through, we can train a machine learning model based on a small subset of the candidates, and then use this trained model to predict the properties of all the remaining candidates at a very low cost, and in fact, with a very small number of candidates. This can further be improved by using active learning. So in the active learning is here used to select essentially the candidates. So rather than doing a random subset selection, you can do active learning methods to also improve the initial sampling process. For example, by taking the most diverse structures, but also a couple of other approaches exist. And that's the second thing we've been looking at intensely for crystal structure predictions, particularly here. Then on the quantum computing side, we also, at the same time, we do a lot of research here. Last year, we have been working on a excited state method, which is NISQ-friendly. So I initially mentioned that we still don't know a lot about the scaling of this methods, and it's true. However, we've been successfully demonstrating on actually QPU as well by now that such methods these variational quantum methods can potentially be used in the near term. The question is still open how they will scale and how they behave if we scale these problems to larger systems. And I guess that's also why Alex, for example, mentioned in his talk that he's not super impressed yet, because many of these methods are still have only been proved and demonstrated on very small systems. Due to the restrictions which we have only very small quantum computers available today. Different research that's with George Booth and also by Jules is a similar method, which is for QCAS-SCF and PT2. Similar as the excited states methods is also just to give us better accuracies, and particularly when we predict excited states and other things. I won't go into much details. Same with George Booth, a collaboration with Hongxiang Chen in our team, where we developed with NPL and also CQC a dynamical mean field theory approach here, which can be executed on a NISQ quantum computer. There are methods which we know work better if you would have a fault-tolerant quantum computer. However, for NISQ regimes, there are not so many, and that's why we also developed this DMFT method. Yeah, just in summary, briefly to recapitulate what I've been saying so far. If you look at computational chemistry, many industrial problems have the requirement that we are sufficiently fast, while accuracy is important but plays a minor role. And this is because we need to evaluate many, many candidates to give the experimentalists a good indication what are the most promising ones. So what we've seen in the talk is that quantum computing cannot on its own really help with this, because in order to tackle these industrial applications, we need to be able to extrapolate the knowledge, meaning the accuracy in the prediction, to many millions of candidates or many millions of computation steps. Based on this, however, and the fact that quantum machine learning has been developing over the last 20 years very successfully, I mentioned and kind of showed that quantum machine learning in combination with quantum computing might be a good long-term strategy, because it might enable us to get good samples, high-quality samples, data sets to train these machine learning models and then hence predict molecular properties, for example, on a large scale. And yeah, with this, I think I can already come to a conclusion. I think I'm a bit under time, so we might have a bit more questions, time for questions. Thanks. Oh yeah, and here's, sorry, the last slide. This is thanks to the team and all the advisors we have, which include Alex and Galvo as well, and of course others. Yeah, thanks, that's it for me.
Okay, thank you so much, Leonard, for this very interesting talk. And well, you're right, we have plenty of time for discussions. First question by Florian Marquardt.
Yeah, so very interesting. So I'm interested in the active learning. So does that mean you look at the, say, learning results from the past few training samples, and then you generate a representation of the best molecule you should now train on? Is that what it works? So what method do you use for the active learning?
So I guess there's this, maybe to distinguish even active learning. So there's this active learning can, I think Alex mentioned this already, can happen in the initial phase. So when you initially sample, get your training set before you even evaluate any, for example, energies to train it on. And it can happen in the later stages. So in the initial phase, there's, of course, because you have only unlabeled data, you would typically use, for example, geometric properties of the, like, for example, how like maximizing the diversity in terms of how close the data points are. While if you also have the energies, depending on the task you want, you can choose the samples, for example, by a range of the energies, or there's many different methods to do this. The method that Gabor, for example, proposed, I think initially, was based on CUR sampling. So what you do there is you take a data set of samples and you create a basis, and with every new, like essentially you want to see the span of this data set. And then with every new incoming sample point, you make a decision whether you take it, you evaluate it or not, is by matching the, looking at what's the overlap of this new data point with the existing data sets. I guess Gabo is maybe even on the call, and he was on earlier, so he might be able to give you more details. But these are.
But that still doesn't sound like as if it depended on somehow your training success. It depends more on diversity, so to speak.
Yes. I mean, exactly. But then, for example, you could also select a distribution of the energies to, like, for example, in crystal structure prediction, when you have you want to train your algorithm to also predict the low energies more accurately, you choose a certain distribution over the energies, and you try to, if you have like a data set which is you have certain energies already evaluated, then you might be able to select these specifically as well.
Okay.
Yeah.
Thank you.
Okay. Further questions? Maybe in the meantime, until people have thought about their questions, let me connect both to your talk and to the previous talk by Alexander. And that is, I mean, that was, of course, the focus of your talk, the establishing really the bridge and putting quantum computing right in perspective in this field. And so the question is, you said quantum computing is not sufficiently fast for many industrial applications. Mm-hmm. And I'm wondering, could you give, well, and also, and that was the previous speaker's point, that so far the demonstration is on very, very small system sizes. But could you, when would you say the methods that have been developed and put forward so far, when would they really provide the right interface for these large scale applications? What is the benchmark? What do you need?
From the quantum computing perspective, or?
Yes, from the quantum computing perspective.
So I suppose that the right benchmark is if you have a higher accuracy prediction at a sufficiently lower cost. Like, for example, if you would be able to really do couple cluster accuracy or beyond that. Mm-hmm. For example, using the algorithm by Ryan and others. If you would have a fault-tolerant quantum computer and you would be able to run these calculations at these sufficiently low cost, right? That would be something where, that's the point at least, where we definitely could say that's valuable. Before that, I think the question is a bit open, because of course, if you would use variational quantum algorithms to achieve a similar accuracy at a sufficiently low cost, then this would be valuable as well. When we're going to reach this is though less clear, because we need to have the right sized quantum computers first to really show that we might actually do something meaningful. And I think that's why it's generally very challenging to speak about performance of variational quantum algorithms, because in the end it's there's little evidence that they scale beyond the 10, 12, 16, maybe 30 qubits they've been demonstrated on the simulator that they perform well. In fact, I think most variational quantum algorithms have only been ever shown to work into a smaller regime. So it's hard to give kind of really scientifically well-funded answers to these questions.
I mean, with the well-known quantum algorithms before, say, the emergence of quantum machine learning, of course, then there was the asymptotic scalar behavior that made a clear statement what is the cost if you go to really large input size. And you're saying that in quantum machine learning and for these variational algorithms, this isn't really established how they scale. Is that what you're saying?
So for variational algorithms, it's not really established, right? Because there's multiple aspects in terms of, for example, the optimizer, how quick you can find the minimum, but also what's the depth of your circuit? Can your circuit actually get into the right accuracy for larger circuit depths, for large problems? It's like these are just questions which are empirically worked for small systems. It's fine, but it's never really investigated. Like Matthias Treuer, I think, did a small paper on the epsilon scaling, for example, the sampling scaling. There's a number of results also which discussed a bit more in depth, but overall they are not really well-funded analysis in terms of the empirical scaling of these methods to larger system sizes. So it's with the big O notation, like if you go to provable quantum algorithms, there's of course challenges on their own. For example, if you have a huge overhead or not, this might come out as well. That it might end like quantum Monte Carlo methods, that the scaling is really nice and low, but in the end we have such a huge overhead, like with the HL algorithm by Aram, that we might not be able to use them in practice. But for them at least, we have the hope, because assuming that the overhead won't be too high, the scaling is sufficiently fast for us to allow to do high accuracy predictions at a low cost in the asymptotic limits. Just to add maybe to Florian, because I just had in my background in my head, just thinking about the question. So one way is also to do active learning, by the way, by doing taking uncertainties into account. So for example, if you have a predictor and you have active like data which you have, and then you see how the predictor matches the actually predicted data, then you can establish uncertainty regions, and based on this you can also inform where you want to sample more, for example, to train your model better. Just as
and there will be a neural network, let's say, that tries to extrapolate the empirically observed uncertainties to a larger space in order to pick new points, or you just try to train again on the samples that you trained on, but you still have a big uncertainty?
Yes, so for example, this would be for neural networks that you can, I mean, there's a bunch of different ways, but for example, you can even do dropout methods. So and then you take what's based on dropouts, what's kind of the variance in terms of the prediction. But depending on the method you use, I mean, for example, if you use more kernel-based methods, you would need to choose other kind of forms of uncertainty prediction. But yeah.
Okay. All right.